Welcome to this video on impulse. Impulse describes the total change in an object's state of motion when a force acts for a very short duration. We will derive the mathematical foundation of the Impulse-Momentum Theorem. Impulse is essentially the push or hit an object receives. It measures how effective a force is at changing an object's motion over time. A small force acting for a long time can have the same effect as a massive force acting for a fraction of a second. Formally, impulse is symbolized by J. It is defined as the product of the average force and the time interval over which it acts. Since force is a vector, impulse is also a vector with a specific direction. The standard SI unit for impulse is the Newton second. When broken down into base units, this equates to kilogram meters per second, which are the same dimensions as momentum. This is the first clue that impulse and momentum are closely related. Our derivation begins with Newton's second law in its most universal form. Force equals the rate of change of momentum. This means force is the derivative of momentum with respect to time, which is our starting point for the impulse theorem. In step 1, we use algebra to rearrange Newton's second law. By moving the infinitesimal time element to the same side as the force, we establish that force multiplied by a small time element equals a small change in the object's momentum. To find the total change over a finite time interval, we perform integration on both sides of the equation. This process sums up all those tiny changes, giving us the total cumulative effect of the force acting throughout the collision. In the final step, the integral of force over time is defined as impulse. The integral of the change in momentum becomes the final momentum minus the initial momentum. The impulse is now shown to be exactly equal to the object's change in momentum. This result is the Impulse-Momentum Theorem, a fundamental law of motion. It states that to change an object's momentum, you must apply an impulse, and the magnitude of that impulse is exactly equal to the momentum change observed. On a force-time graph, the area under the curve is the impulse. Real-world forces are not constant during a collision, rising and falling in a spike. Calculating the total area under this spike gives you the total impulse. We often use the concept of an average force to simplify calculations for complex collisions. The average force is constant over the collision time and produces the same total impulse as the actual varying force profile. In sports, athletes follow through to maximize momentum change. By increasing the time of contact, they increase the total impulse delivered to the ball, making it fly faster and further, even if the average force remains the same. In safety applications like car crashes, the change in momentum is fixed. Airbags save lives by increasing the duration of the stop. By increasing the time, the average force on the body is reduced to a survivable level. Automotive crumple zones apply the same principle. The deliberate crushing of the car frame extends the impact time. This prevents the instantaneous stop that would otherwise result in a lethal force. Boxing gloves are a final case study. Bare fists create high peak force over a short time. Gloves add padding to compress over a longer time, resulting in a lower peak force, reducing the opponent's injury severity. Manual impulse control is used when catching a fastball. Cricketers or baseball players pull their hands back with the ball to increase the contact time. This extended time reduces the force felt, avoiding a painful sting. Bending your knees when landing from a jump is an application of biological shock absorption. This action increases the collision time, lowering the impact force on your bones and joints, preventing injury. For forces that vary with time, we use calculus to find the exact impulse. The integral of force over time sums up millisecond by millisecond changes during a collision to find the total momentum change. In safety engineering, a hard, sudden hit is represented by a tall, short force spike. A soft, padded hit is a wide, low curve. Both represent the same total impulse, but the wide curve saves lives by reducing the peak force. Impulse is mathematically linked to momentum through mass and velocity change. It equals the mass times the difference between the final and initial velocities. If an object stops, the impulse equals mass times its initial speed. Direction matters for impulse. If a ball bounces back from a wall at the same speed, the change in momentum is double what it would be if it simply stopped. This requires twice the impulse. When firing a bullet, the explosion provides an identical impulse in opposite directions to the bullet and the gun. The gun's backward impulse is called recoil, adhering to the conservation of momentum. In industrial applications, water jets cut steel by applying continuous impulse. The constant change in the water's momentum as it hits the surface generates enough force to slice through metal. A hammer provides a mechanical advantage. By swinging the hammer, you give it momentum. When it stops abruptly against a nail, the tiny stopping distance creates a massive average force. Falling on a soft surface like sand is safer than concrete because the surface deforms. This gives you extra time and distance to stop, dramatically lowering the peak impact force on your body. Rockets utilize spaceflight impulse by ejecting mass. The constant impulse generated by the exhaust gases creates the thrust needed to accelerate in a vacuum and reach orbit. Speed is critical for destruction. While momentum is linear with velocity, the energy required to stop an object increases quadratically. Impulse helps engineers design barriers to absorb this exponential increase in energy. Gravity provides a constant force, or weight. The longer an object falls, the more time gravity has to apply impulse, resulting in higher final momentum at impact. In solid objects, impulse travels as a mechanical shock wave. The speed of this wave, which is the speed of sound in the material, determines how the force is distributed throughout the object. During internal collisions, such as two objects pushing off each other, the impulse on one is equal and opposite to the impulse on the other. This ensures that the total system momentum remains zero. Real-world systems are rarely perfectly isolated. External impulses like friction and air resistance provide continuous backward impulse that gradually cancels out forward momentum, eventually causing any moving object to stop. A bike helmet acts as an impulse management device. The foam crushes upon impact, extending the deceleration time for the brain. This action lowers the peak force below the critical threshold for a concussion. Even at the atomic level, impulse is key. In particle accelerators, the transfer of momentum during collisions, which is effectively the impulse exchanged, helps us understand fundamental forces. A jet engine is a momentum machine. It provides a massive backward impulse to a stream of air. The forward reaction force, or thrust, is the result of this constant impulse, allowing the plane to maintain speed. Impulse can be destructive on a tiny scale. In boat propellers, collapsing water bubbles create microscopic, supersonic impulses. This phenomenon, known as cavitation, can pit and destroy solid steel over time. To validate the Impulse-Momentum Theorem mathematically, we check the units. Force times time, in Newton seconds, breaks down to kilogram meters per second, exactly matching the units of momentum. The proof is verified. In physics, time is everything. A short stopping time leads to a deadly force, while a large stopping time results in a manageable force. This realization is the basis of every modern safety device. This Mastery Toolkit table summarizes the relationship between impulse, momentum, and force. Use these formulas to calculate collision forces, from simple impacts to complex physics scenarios. Impulse is the universal language of physical interaction. It is the vital bridge between the world of forces and the world of motion, governing everything from particle collisions to rocket science.